the non-healing cells into a healing cell. So in summary, I will not read it, but in general, that there is a distinct population within the chronic wound that has a healing potential and that is linked to clear clinical outcomes in patients, and this loss of the signals of control and are really not only coming for what we knew already about high protease activity, but also decrease of receptors that mediate signaling. There are signaling molecules that mediate the signals in the cell, and obviously increase in microRNA molecules. And obviously one approach would be to
and look at epigenetic effects. Well, this is basically ABY hypomethylation, or if you want to think about it as yellow mice going this way. We have increased numbers of brown mice and decreases in hypomethylation or increases in hypermethylation. So what you have is a curve that goes like this. And we think, only guesstimating, because at 7.6 centigrade it looks like it's going back. This curve is crossing 0, 0 somewhere at 10 centigrade or above, somewhere in here, and then goes up into the higher doses where other investigators have uniformly seen hypomethylation and also a sex effect that is more prevalent in males than in females. This sort of biphasic dose-response curve or hockey-shaped dose-response curve is consistent with a hormetic dose-response curve, but it is not consistent with the linear no threshold model, which says that every dose of radiation is problematic. This is surely not the case when you're looking at epigenetic changes. So questions in future studies. These are my sort of biases and things that I think are going to be important to do in the future. One question is, does low-dose radiation exposure alter the human epigenome? Remember, all of this was done in mice, and we've only looked at one metastable epiallele. Another big question, if yes, are the changes in the epigenome inherited transgenerationally? It's a big, big issue. Big question. So how do you do this? I believe that the best human populations for addressing these critically important questions are going to be the Hiroshima and Nagasaki atomic bomb survivors and their offspring. These are available, and I think we need to think seriously about looking at them from the standpoint of epigenetic modifications. I now want to end it, this is the last slide, with a slide that I call food for thought. Something that you will be able to chew on and think about after you leave this lecture. One of them is a quote by a physicist and the other by a philosopher. The physicist is John Cameron at the University of Wisconsin, who developed the first solid-state lithium fluoride radiation detector system and also started the very first radiation health physics department at the UW. And later towards the end of his life, he wrote this: I am now almost certain that we need more radiation for better health. And the second quote, what does not kill me makes me stronger.
from some of the studies from the famine and also your mouse model. So is the process you are suggesting is reversible in mid-phase after some mutations, like me, say, or early stage of me? Could it be affected by some of the antioxidant effects?
In other words, you're saying an adult animal that has, let's say, a negative effect, can you reverse that?
Yes.
In adult animals? That's an excellent question. To my knowledge, nobody's looked at it. We've always done work with the basically developing fetus and the programming there, but we've never actually addressed the question that you're talking about. And it's very important, and if anybody's interested in doing this, I wish somebody would, because when other people ask this question, I would be able to answer it.
And the second question regarding the Hiroshima and the Nagasaki effect, that has probably one of the most studied population in terms of radiation exposure and the effect on all the issues related to cancer and other changes. So did anybody look at the degree of methylation of some of the genes